Understood, sir.
All right. Okay. Now let's look at this one. Right, flow through an orifice. Right, and then we'll discuss Bernoulli's theorem or Bernoulli's principle, as well as the what do you call this? The continuity equation. Right. In N4, the continuity equation, or in N4, in fact, we only looked at pipes in series. Right. For fluid mechanics, we also look at pipes in parallel. Hence, how we calculate or how we use the continuity equation is going to be a bit different, right? Based on the kind of pipeline system you are looking at. So it's pipe in series. We're going to use it the same way we did in N4, and then if the pipes are in parallel, I'm going to show you how you use the continuity equation. Right. For now, though, let us look at and understand how the equations we use for flow through an orifice come about, right? Now that we're going to do through using this diagram, right? So flow through an orifice is where you have a reservoir, right? And then on the side of the reservoir, an orifice is fitted onto it, right? Now, for the most part, that orifice will be circular in shape, right? So if you look here, you have a reservoir, right? And then the reservoir is fitted with an orifice on the side, right? So the orifice is essentially where the water is coming out from the reservoir. Right? That is what an orifice is essentially. Right? Now, as far as theoretical findings, right, or the difference between theoretical findings and actual findings is that with theoretical findings, we normally just use mathematical equations, right, to calculate theoretical findings. Whereas with actual findings, it is findings that we get through the means of graphs, right? It is through the means of graphs, right? Hence, if you look at how we calculate the theoretical velocity, right, we essentially applied Bernoulli's between 2 points, right? Now, with Bernoulli's theorem is essentially when you've been asked to define Bernoulli's theorem, right? You can define it in a number of ways, right? The most common one is using the fact that Bernoulli's theorem is based on the conservation of energy, right? Bernoulli's theorem is a mathematical expression of the conservation of energy between any 2 points in a fluid's motion. Right? That's the most basic way of defining Bernoulli's principle, right? So Bernoulli's principle, it's a mathematical expression, right, of the conservation of energy between any 2 points in a fluid's motion, right? So if the fluid is in motion, right, if you have a fluid and it's in motion, right, energy is being conserved, and that energy or the energy conservation thereof, right, we express using Bernoulli's theorem, right? With Bernoulli's theorem, you essentially, if we assume that the system is 100% efficient, so there are no losses, right? We know that is impossible, right? But for having to explain the concept, we assume that the system is 100% efficient, so there are no losses, no shock losses, no losses due to friction, right? We ignore all of those losses, right? And as such, with Bernoulli's theorem, right, we essentially look at 3 energies, right? So the first one here, right, this represents the pressure energy, this one represents the kinetic energy, and this represents the potential energy, right? So what we do is, in flow through an orifice, we apply Bernoulli's between 2 points, right? And the points that we apply Bernoulli's, right, are point 1 and point 2. Now, if you look at these 2 points, right, if you look at these 2 points, they are coaxial, right? Meaning that they are on the same center line, right? This point here in particular, right, is called the vena contractor. Right, this point here is called the vena contractor. Now, the vena contractor is essentially the when the water escapes from the reservoir through the orifice, right? It jets out of the orifice, right? Now, when it does that, before falling to the ground, right, there is a point where the water jet is the least in terms of diameter or is the least in terms of area, right, before it starts falling to the ground. So that point where the water jet has the least diameter or the least area before it falls down to the ground, right, that point is the point that we refer to as the vena contractor, right? And the vena contractor, right, the vena contractor or the diameter or the area thereof is the one that we refer to as the actual area. Because in doing all of this, we're essentially investigating what happens at this point, right? Hence, it's being referred to as the actual diameter, right? As well as the even the what is this the actual findings, right? The actual findings will be the findings that we get at this point, right? When now we are considering everything, right? When we assume that the system is perfect, as in the system is 100% efficient, right? When applying Bernoulli's between the 2 points, right, the velocity or the findings that we're going to get are going to be theoretical, right? So meaning in having to apply Bernoulli's between these 2 points, assuming that there are no losses, right? Whatever we get will be theoretical findings, right? Whereas when we apply Bernoulli's, right, also considering some losses or considering whatever losses that occur, right, be it frictional losses and right, whichever losses that occur, if we consider them, then whatever velocity that we get will be the actual velocity, because essentially we are considering losses as well, right? So it is not essentially an ideal case, right? Only when we look at the flow of the water ideally, so meaning that not considering any losses, right, is when we say that we have whatever findings we get are theoretical, right? So as far as the difference between theoretical and actual findings, but the difference is that with actual findings, we look at the jet from a perspective of the jet or the system being 100% efficient, meaning that we are not considering losses. Hence, we only apply Bernoulli's theorem, which is a mathematical expression, right? Hence, whatever we get there will be theoretical. Whereas with actual findings, right, we essentially use the graph, right? We tabulate our information, use the graph, but remember the what is this? What do they call this thing? Motion graphs. Yes. Do you guys remember motion graphs from engineering science?
That with the lines, the straight lines, and then you must do the angles.
So motion graphs, I'm referring to the displacement time graphs, the velocity time graphs.
Oh yeah, I remember that. Yeah.
Yeah. So with actual findings, right, or let's say with theoretical findings, we use mathematical expressions, right? And for having to calculate the theoretical velocity, right, the mathematical expression that we use is through the use of Bernoulli's theorem, right? And we look at it ideally, meaning we assume that the system is 100% efficient, right? Whereas with actual findings or the actual velocity, we use motion graphs. Now, in the absence of motion graphs, we are able to use equations of motion, right? So remember that equations of motion are derived from motion graphs, right? So because we don't necessarily draw graphs, we're able to use equations of motion. And because we are using or because we are able to use equations of motion, right? Using equations of motion is the same as using motion graphs. Hence, whatever you get using equations of motion, right, will be actual findings. So that's the difference between the two, right? Now, in saying that, remember I mentioned that theoretical findings. So, for instance, how we calculate or how we derive the formula to calculate the theoretical velocity, right, is through looking at the flow through an orifice ideally, right? So, meaning not considering losses, right? And we come up with this equation, right? I'll explain it just now. Now, we are also able to calculate the what is this, the actual velocity, right? But only using Bernoulli's theorem, but now considering losses. Right? So essentially meaning that when considering losses, right? So whatever velocity that you get, so V2 here, right, will not longer be theoretical, it will be the actual velocity, because now you are considering losses as well. Right? But that I will explain later when we look at a problem where we are considering losses. Right? The point here though is both the theoretical and actual findings are of this point, the vena contractor. Right? The only difference is that the theoretical findings we get through the use of mathematical expressions, whereas the actual findings we get through the use of motion graphs. Right? Because we do not necessarily use motion graphs, we use equations of motion instead. Does it make sense?
Yes, sir. So by the actual findings, we just use the equations.
So with actual findings, right?
Yes.
I'll get to it. But how this formula comes about, right? It is through the use of equations of motion.
Okay.
You see this VA here?
Yes, sir.
Right. So this formula, right? The actual how you calculate or how you derive the actual velocity, right? It is through the use of equations of motion.
Okay.
Yeah, it is through the use of equations of motion. All right. So let us first look at how we calculate the theoretical velocity, or how the formula to calculate the theoretical velocity comes about. Yeah.
Okay.
All right. So like I said, with theoretical findings, right, we use mathematical expressions. Right, and the mathematical expression that we use is Bernoulli's principle. Right. So like I said, Bernoulli's principle, right, is the mathematical expression of the conservation of energy, right, of a fluid in motion. Right. So what you do essentially is we are able to apply Bernoulli's between any 2 points, right, in the fluid's motion. Right. If you have a fluid and it's in motion, you are able to apply Bernoulli's, right, between any 2 points. So by between any 2 points, you can apply Bernoulli's. You can apply Bernoulli's between this point and this point. You can apply Bernoulli's between this point and any points here, right? So between any 2 points in a fluid's motion, you are able to apply Bernoulli's, right? So you use the points that are most convenient for you to use.
So sorry, sir. So does it matter if the 2 points is in a straight line or at the angle? Doesn't matter.
Doesn't matter.
Okay.
Doesn't matter. Right. For instance, you could have something like this. Right. You could have a reservoir. Right. And this reservoir is filled with water. Right. And then have a pipe coming into the reservoir that goes in this direction. Right. So if it happens that maybe you have enough information at this point, called this point 1, and the other information you have is at this point, called this point 2. Right? You can apply Bernoulli's between this point and this point. You see what I'm saying?
Yes, sir.
Also, you are able to apply Bernoulli's, right? Say this is point 3, right? You will also be able to apply Bernoulli's between point 1 and point 3, right? Or point 2 and point 3, right? So between any 2 points, right, in the fluid's motion, you are able to apply Bernoulli's. Any 2 points. Are we clear?
Yes, sir. I understand now. Yeah.
Right. So again, you are able to apply Bernoulli's, or we apply Bernoulli's between any 2 points in the fluid's motion, any 2 points. Right. So if it happens like in this example, right? Say you are looking for some quantity at this point, right? And you have enough information at this point, right? And based on what you have, it is convenient for you to apply Bernoulli's between this point and this point, then that is exactly what you do, right? So between any 2 points, right, you apply Bernoulli's between any 2 points, right, that are most convenient, right, for you to use. Nah.
Yes, sir. But it's probably going to be best to use the 2 points that has the most information.
Yes. So when I say that are the points that are most convenient to use, that is exactly what I'm referring to. So points where you have the most information.
Yes, sir. Okay.
Yes. Beautiful. Right. Now let us see how the formula for calculating the theoretical velocity comes about. Right. Bearing in mind that whichever findings, be it theoretical or actual, right, those findings are going to be of the vena contractor. Right. So the theoretical velocity, right, is essentially V2, VA, but the actual velocity is also V2.
Thank you, Lekki.
Just to prove it real.
Okay.
Real people don't know.
Thank you.
Right. What was I saying? So both the theoretical and actual findings, right, are of this point here, the vena contractor. Right. Hence, once you've calculated the actual velocity, right? Once you've calculated the actual velocity, so say you've calculated the actual velocity using this equation, right? Or any other equation that you are able to calculate the actual velocity using, right? Once you've calculated VA, right, you are able to apply Bernoulli's again between these 2 points, right? But now considering, say, frictional losses, for instance, right? When considering frictional losses, for instance, right, the V2 is no longer theoretical, but it is actual. Right? That is the part I want you guys to get, that with both theoretical and actual velocity, right, they are of this point. So both of them are V2. Right? So the difference is that when having to apply Bernoulli's between 2 points and you're looking at it from an ideal perspective, so meaning you're not considering losses, then the V2 is theoretical. But when applying Bernoulli's between these 2 points, right, but now considering losses, then the V2 becomes actual velocity. Are we clear?
Sorry, sir. My internet went blank now, but I'm back.
All right. So let me go over that again.
Hello.
Can you hear me? Leroux?
Hello, sir. Can you hear me?
I can hear you. Can you hear me?
Yes,
Can
sir.
you
Can
just
you?
repeat that, please? So we both lost connection.
All right. So I'll go over that again. Can you both hear me now?
Yes,
Yes,
sir.
sir. Can hear you.
Right. So what I was saying is both the theoretical and actual findings, right, are of this point, the vena contractor. Right, so both the theoretical velocity and actual velocity are both V2. Right. So the difference is that when applying Bernoulli's between these 2 points, right, when looking at or when applying Bernoulli's from an ideal perspective, so meaning that not considering losses, then the V2 is theoretical. But when applying Bernoulli's between the same 2 points, right, but now considering losses, so for instance, if we were to consider frictional head losses, then we'd have plus rho G HF here, right? When considering losses, then V2 in that case is now the actual velocity. Are we clear?
Yes, sir.
So you said Bernoulli's without losses, we use V2.
So Bernoulli's without losses, so like that. Bernoulli's without losses, so meaning we are looking at this ideally, then V2, right? The V2 that you are going to use or the V2 that you're going to calculate here or get will be the theoretical velocity. Right? And then when considering losses, right? So for instance, if you're considering or if the losses to consider are only frictional head losses, right? Then the V2 will now be expressed in terms of actual velocity. Are we clear?
Yes, sir.
Right. So in coming up with formula for calculating the theoretical velocity, right? We look at this ideally. So meaning we do not consider losses. Hence, when applying Bernoulli's between the 2 points that are coaxial, right? So these 2 points are sharing a center line. Right? We only consider the pressure energy, the kinetic energy, as well as the potential energy. Right? Now, it is important to note that with in flow through an orifice, right, or in applying Bernoulli's, right, because remember you get different types of pressures. You get the absolute pressure, you get atmospheric pressure, right, and you get gauge pressures. Right, in the application of Bernoulli's, right, the pressure that we are interested in is gauge pressure, right? So not atmospheric pressure, definitely not absolute pressure, right? So the pressure here, right? So meaning when referring to P1 or P2, we are referring to gauge pressure, not atmospheric pressure, not absolute pressure or total pressure. Right? Right, so in applying the leverage between the 2 points, we have P1, right? This is, now, I don't know if you guys went through the documents I sent on the different variations of Bernoulli's equation. Did I send the documents?
Yes, you send the one with a few pages with the different, when it's different diameters.
Right.
How the equation changes then.
Yes. So from that document, you can see how we are able to express Bernoulli's equation, right? So we have 3 variations of Bernoulli's equation, right? And each of the variations is specific to some kind of energy, right? So this one in particular, right? This one in particular, each of these terms are in terms of what is this, Pascal. So P1 being P1 will be in terms of Pascal. This term will also be in terms of Pascal. This term will also be in terms of Pascals. right? So you get a variation that is relevant or that is convenient for calculating pressure. You get a variation of Bernoulli's equation that is convenient for calculating velocity, and you get one that is convenient for calculating height. So if you go through that document, you will see exactly what I mean by those three variations, right? Now, it doesn't matter which variation you use, right? I showed you those three variations for convenience, right? For convenience, meaning it is best, or I find it best to use the appropriate, or to use the variation of Bernoulli's equation based on what it is that you are looking for. Right? So if you're looking for pressure, this is the one I prefer using, right? Because you don't have to do too much manipulation. And then you get one for velocity, and then you get one for what is this, height as well. Right? Right. So you have P1 plus the kinetic energy in point 1 and potential energy in point 1. And then you get the same for point 2. Right? P2, the kinetic energy as well as the potential energy at point 2. Right? Now, because the 2 points, right, in the 2 points are coaxial, right? It means they are the same height from the ground, right? Which means that as far as potential energy, they will have the same potential energy. That is why these two have been cancelled, because essentially H1 and H2 are equal, right? And then as far as the as far as the kinetic energy, right, for V1, or the kinetic energy at this point, which is inside the reservoir, right? So it is said that because the orifice, or the diameter thereof, or the area thereof, is too small relative to the size of the reservoir, right? The velocity that the water is moving, right, in the reservoir is so small that it doesn't make any impact on our calculations, right? So meaning that the velocity at this point, which is inside so the velocity anywhere inside the reservoir, right, is so small that it has zero impact on our calculations. Hence, we take it as being negligible. Taking it as negligible means that, right, you take it as being approximately equal to 0. Right, so the velocity of the water inside the reservoir, right, will always be approximately equal to 0. Right, that is why this term goes away, because essentially V1, which is the velocity inside the reservoir, is equal to 0. So that falls away. Right, and then P1 will have some value of P1. Right, because remember, with what is this, with pressure in a fluid, right, we are able to calculate gauge pressure in the fluid as long as the fluid is at some height h from the water level, right? So if you look at this point, right, this point is at some height h from the water level, so you're going to have some value of pressure at this point, gauge pressure, that is. Right, and then as far as P2 is at this point, right? Now P2, if you look at P2, right, it is water exposed to the atmosphere, right? There is no column of fluid above this point. So just like how we have a column of fluid above this point, which is this column of fluid H, there is no column of fluid above this point. Hence, the gauge pressure at this point is approximately equal to 0. And like I said, as much as you would have atmospheric pressure at this point, right, we are not necessarily interested in atmospheric pressure. That is why this falls away, because the gauge pressure at point 2 is approximately equal to 0. Why is it equal to 0? Because essentially there is no column of fluid above this point. right? Remember that pressure is equal to rho GH, right? So if the H is 0, it means the pressure is 0, right? And this H is the height above that point, right? So the H refers to the height or the column of fluid above the point you are looking at. So if you're looking at point 1, right, the height we're interested in is not this one, right? This one is for potential energy, but the height, so the height below, right, the height below the point is for potential energy, whereas the height above the point to the water level, right, that H is for gauge pressure. We refer to that H as a column of fluid, or the height of the fluid above the point you are looking at. Right? That's why we have, or that's why we'll have a value of P1 at this point, because there is a column of fluid above point 1, whereas in point 2, there is no column of fluid essentially above this point. Hence, H for P2, right, will be approximately equal to 0. If it's equal to 0, then it means P2 is also equal to 0. That is why this term falls away. Right, and then of course you are going to have some velocity of the water jet at this point. Right, hence this term you leave exactly as it is. Right, so like I explained, V1 is approximately equal to 0. Right, so any velocity of the fluid inside the reservoir will always be equal to 1, be it 0.1, even 0.2, even 0.3. The velocity there will be equal to 0, right? So anywhere in the reservoir, the velocity we take as being approximately equal to 0. Right? Hence, that is why V1 is equal to 0. Right? P2 is atmospheric, right? And we are not interested in atmospheric pressure. The gauge pressure there is approximately equal to 0. That is why this falls away. Right? And then I also mentioned that seeing that 0.1 and 0.2 are coaxial, it means they are at the same height, right, to the ground. Hence, these terms will be equal. Hence, they cancel mathematically. Right, so meaning that essentially you'll be left with P1 is equal to half rho V2 squared. Right, and as we've established that how we would calculate P1, right, is by using this rho GH. Right, the H is the column of fluid above the point. So this H here. Right, so that is where this here comes about. So here you would have, so from this step, you would then have rho GH is equal to half rho V2 squared, right? And then of course, the rho of water is the same. So mathematically, this and this is going to cancel. Right, and then bearing in mind that we are trying to make V2 the subject of the formula. Right, in doing that, you will then multiply both sides by 2. Right, that is where this comes from. Right, multiplying both sides by 2, you would then have V2 squared is equal to 2 GH. Right, again, you're trying to make V2 the subject, hence you apply the square roots for both sides. Right, so applying the square roots for both sides, right, obviously this and this will cancel, right, and then if that cancels, you'll only be left with V2, hence V2 will be equal to the square root of 2GH. That is where this comes from. Right, now how we applied Bernoulli's here is from an ideal perspective, meaning that you didn't consider any losses. So meaning that this V2 is what is theoretical. And that is how we get the formula for calculating the theoretical velocity. Right, so the theoretical velocity of the fluid or of the jet is equal to the square root of 2gh. This h here, right, refers to the column of fluid above this point.
So, sir, if we want to use that formula, do we have to show that whole calculation, or
Nah,
so we can just use the formula?
you can just use the formula. Right.
Okay.
So the reason why I wanted to explain the formula is so that you understand where this h comes from.
Okay, I understand.
And that's why I made the h different, right? I made it a capital letter H so that you know it's different from H1 or H2. Right? So this H represents, right, this the column of fluid above that point. Right? So if you have that H, essentially it means you can get the theoretical velocity. Right? And then as far as the actual velocity, right? So the actual velocity, this is the equation we use, which is derived from having to use the equations of motion, right? So the x here stands for this horizontal distance of the jet, right? So when the water jets from the orifice, right, from the point that it jets from the orifice to where it lands, the horizontal distance is the x distance that we use in this equation. But similarly with the y measurement or y value, that is essentially the vertical distance of the jet. Right, so from the vena contractor to the ground, that is your vertical distance of the jet. Right, and that's what you use here. And whatever you get here will give you the actual velocity. Are we still together?
Yes, sir.
Yes.
Right. So that is the actual and theoretical velocities. That is how you calculate them. Right. As far as the theoretical and actual diameters. Right. So the actual diameter would be the diameter of the vena contractor. Right. So if you've been given the diameter of the vena contractor, that is the diameter that you take as your actual diameter. Right. Whereas the theoretical diameter, right, that one we take as the diameter of the orifice. Right, so that's the difference between the two. The diameter of the orifice is the theoretical diameter, whereas the diameter of the vena contractor is the actual diameter. Right? Hence here are labeled dt as being the diameter of the orifice, and dA, which is the actual diameter, will be the diameter of the vena contractor. Right, that is where these two come from. Right? As far as how you calculate the area, right, the area of the orifice will be circular. The area of the vena contractor also we also take it as being circular. Hence, when having to calculate the area for either of those, right, you use the cross-sectional area to calculate a circle, which can be pi over 4 times d squared or pi r squared. Right? Any questions?
No. No, sir.
Okay.
Nothing from my side.
Okay. All right, let's look at hydraulic coefficients. Now we get 3 hydraulic coefficients. Right, you get the coefficient of velocity, you get the coefficient of contraction, as well as the coefficient of discharge. Right, so now each of these coefficients, how we express them mathematically, right, will always be actual over theoretical. So meaning that, for instance, if you look at the coefficient of velocity, denoted as CV. To calculate CV, right, this coefficient is based on the theoretical and actual velocities. Right, so when I say your hydraulic coefficients, how you calculate them or how you express them mathematically will always be in terms of actual as the numerator and theoretical as the denominator. Hence, if you look at how we calculate CV, the coefficient of velocity, right, it is the actual velocity divided by the theoretical velocity. Right, and how we calculate the coefficient of contraction, right? So contraction refers to the changes in diameter, right? Even this hydraulic coefficient is also in terms of actual divided by theoretical. So all the hydraulic coefficients are in terms of actual, or are a ratio between the actual and theoretical findings. Actual being the numerator and the theoretical being the denominator. Right. Now, the coefficient of contraction is the actual area divided by the theoretical area. Right. Now, this one will essentially be based on, or how you calculate this one will be based on what you've been given. If the areas have been given and you don't necessarily have to calculate them, then you can just use the areas. So you use the actual area divided by the theoretical area that you've been given. Or if, for instance, you've been given the area of 1, so meaning, for instance, if you've been given the theoretical area, so you'd substitute the theoretical area as it is, and you'd have to calculate the actual area. Whereas,
but then they'll have to be the coefficient.
Second?
If they give you, like Sir said now, they give you one area, and then they'll have to give you the coefficient already in order to get the, say you need to calculate the theoretical area, they need to give you the coefficient already in order to calculate the actual area.
So they can do that, or they can give you the diameter, and you can work out the area.
Okay, then you just,
Yeah.
Understood.
Right. So if neither of these areas has been given, and instead you've been given their diameters, so you've been given the actual diameter as well as the theoretical diameter. So meaning actual diameter being the diameter of the vena contractor, theoretical diameter being the diameter of the orifice. So if you've been given both those diameters, then you can just use this equation here. Right?
Okay.
Because if you look at how this works out mathematically, these two are going to cancel. Hence, you can just use the diameter, the actual diameter squared divided by the theoretical diameter squared. That will also give you an equivalence of the coefficient of contraction. So meaning that if you've been given the diameters, instead of having to calculate the areas, you can just square the diameters.
Oh, yeah.
You see what I'm saying?
Yes, sir.
Right. And then we get the coefficient of discharge, CD. Right. Discharge is the flow rate. The flow rate, which is denoted as Q. Right. So the flow rate can be, right, they can call it in different terms. They can call it the discharge, they can call it the flow rate. Right. Sometimes it can be referred to as the volumetric flow rate. So all of that is the same thing, Q. Right. So how we calculate the coefficient of discharge, which is denoted as CD, is through using the actual flow rate divided by the theoretical flow rate. Hence the QA over QT. Right. How we calculate the flow rate in general is by using this here. Right. So V times the area. So for the actual flow rate, we then use the actual velocity times the actual area, which will give us QA. For the theoretical flow rate or theoretical discharge, we would use the theoretical velocity multiplied by the theoretical area, which will give us QT. Right. So if it happens that you've calculated both QA and QT, you can just use this formula to get CD. Right. But also, seeing that we've established that QA is equal to VA times the actual area, and QT being equal to VT times the theoretical area, right? Which, if you substitute that as it is, this is what we get. Right? And then separating the terms, right? Separating the terms like so. So having VA over VT times the actual area divided by the theoretical area, hence having this. Right? We've established that VA over VT is equal to CV, and the actual area divided by the theoretical area is actually equal to the coefficient of contraction. That means that we are able to calculate CD using the product of these two. Right, so meaning if, say, you haven't calculated any of the Qs, but you've already calculated CV and CC, right, you can just multiply those to get CD. Right, so you can get C3, you can get CD through the use of this formula, or you can get it through the use of this formula, whichever one is convenient. Right, so obviously, if you've already calculated CV and CC, then it is convenient to just use this to calculate CD. Any questions?
No, sir.
No,
Right.
no, sir.
Right, so now you can look at these examples. Now you can look at this. I've included the solutions to them, right? So I would say first try them on your own, right? And then if you get stuck, you can either ask me or you can refer to the solutions to see where you went wrong, right? But first try them without referring to the solutions, right? Just see if you understood how we go about looking at flow through an orifice, right? And then you can use the solutions to check your answers, right?
So, sir, for test 2, we only gonna have a look at flow through an orifice, not the puppet tube. We're not gonna look at the puppet tube
Peter tube.
Because there's an orifice plate, then there's the puppet tube, then there's the orifice also.
Yeah, so
We only
only the
look at the orifice.
Only the orifice, yes.
Okay.
In fact, because you're using a different textbook, did I send you guys the syllabus?
No, I don't know if Rika's got it, but I don't.
Okay, I'll send you guys the syllabus as well. In fact, before I do, because I want us to look at how we would then how we would apply Bernoulli's, right, and how it affects how we look at V2 if we are now considering losses, right? But we'll do that just now.
Okay. So, but the losses only comes in by chapter 8, the flow through the pipes or the flow in the pipes.
Okay, so the reason why I'm going to the textbook is because you are still using the old textbook, the red one, right?
The red, yes, this is the recommended one according to college.
Okay, so that textbook is essentially an old textbook. For instance, if you look here on your textbook, I'm thinking module, I think module 7 and 9 are the same, are in the same module. Because instead of having flow through an orifice, I think you have measurement of flow.
Yeah, we have measurement of flow, which is 7, and then flow through
an orifice.
That's module 9.
Yeah.
Yeah. So we are going to look. So from looking at looking at the new syllabus, right? For the second assessment, we'll look at module 6, 8, and 9.
6, 8, and 9.
So 6, 8, and 9.
6, 8, and 9, yeah.
Keep it for there, so. Because the books, our books is completely, chapter 9 is the jet.
Yeah.
The impulse jet. It's completely confusing.
Yeah. Well, I understand. So there's an updated syllabus for fluid mechanics, 5 and 6. Hence the new textbooks.
So how are we gonna get the new editions, sir? Must we buy that on the Future Manager, or
what is this now?
The new
syllabus or textbook?
Yeah.
The new textbook.
Yes, sir.
Well, you don't have to buy the new textbook because I mean you, Leroux. I borrowed you the relevant textbook.
Oh, so this is the new textbook.
That is the new one.
Okay.
Right. So I only had one.
Okay, sir.
Yeah, I only had one. But the red one isn't irrelevant. Both textbooks are written by the same author. Right. So the red textbook isn't irrelevant. It's just the split of modules is different. Just only difference, really. Nah.
Okay. Okay, sir. But I'll just go according the notes that you've sent in the old question papers that you sent, and then compare to the red book that I've got.
Yeah. Right. Okay. The red book is definitely relevant. Right. Hence I'm saying it is both books are written by the same author. Oh, right. I also have the red textbook. So if you have questions on the red textbook, right, you can let me know. It's fine.
Okay. Okay. Thank you.
Right. Right. Just remind me to send you guys. In fact, after the session, I'll send you guys the syllabus. I thought I sent the syllabus a long time ago. Right. Now I want us to look at, right, if we're no longer looking at applying Bernoulli's from an ideal perspective, how that would affect V2, or how we would then use our Bernoulli's. Right. So say applying Bernoulli's between the same 2 points, but now considering losses. So say we are considering frictional head losses, HF. Right. HF stands for frictional head losses. Right. The introduction of the frictional head losses or any type of losses, right, means that we are no longer looking at the 2 points from an ideal perspective. Hence, this is no longer theoretical, right? Because there is no such system as 100% efficient, as a 100% efficient system. So when we say a system is 100% efficient, right? We essentially mean that we are looking at the system from an ideal perspective, which can never be the case, right? So meaning when considering losses, it means you're no longer looking at the system from an ideal perspective. Hence, the V, so V2 is no longer theoretical, but it is the actual velocity, right? So the kind of problems you will be dealing with, right? You will be asked to calculate, say, any one of these two, right? Any one of, right, either HF or P1, right? My point here is that V2, right, will now be VA. Am I making sense here? Right. So because we are considering losses, right, V2 will no longer be theoretical. So you won't substitute V2 as VT, but you will substitute it as VA. Right. At this point, you will have calculated probably both the theoretical and actual velocities. Right. But because of this here, right, but because we are considering losses now, right, it means V2 is no longer theoretical, but we are looking at seeing that this is no longer an ideal perspective, right? The V2 we will substitute as VA. So that is what I meant by both theoretical and actual being findings of the vena contractor, right? Meaning both VT and VA being V2. Right, there is a problem like that where you have to calculate, for instance, HF. Right, they tell you that the system is experiencing frictional head losses, right? And you're asked to calculate those frictional head losses, right? So essentially HF, right? So from this here, what you would then do, so here you'll be left with P1 is equal to, so this will be half rho VA squared plus rho G HF, right? And then this we're able to express in terms of the formula for calculating gauge pressure, right? Remember to calculate gauge pressure, right? We use rho G and then H, which is the column of fluid above 0.1, right? Is equal to half rho VA squared plus rho G HF. Right? Obviously, the rho is the same, so the density. So this is the same. So this is going to cancel. Right? And essentially, these are the terms that you are left with. Right? And because you're looking for HF, you then transpose this term to that side, right? And divide by G to make HF the subject of the formula. Right? Hence, to get HF, right, you transpose this term to that side, and you'll have GH minus half VA squared, right? And then you divide by G. Right, divide by G. So this divided by G. Essentially, this will be equal to GH divided by G minus VA squared divided by 2G. All right, obviously, this and that cancels. Right, hence to calculate HF, HF will then be equal to that. Right, now in calculating when looking at flow through an orifice, when having to calculate frictional head losses, right, you don't have to apply Bernoulli's, because you know that in applying Bernoulli's, right, you are going to come to this equation, right? So you can use this as an equation. Right, so HF essentially is equal to, right, H, which is that height or column of fluid above 0.1, right, minus VA squared divided by 2G. Right, so that is to say, therefore, HF is equal to this. Right, you can use this as an equation. Right, what you'll see with fluid mechanics, most of the modules make use of Bernoulli's equations. So if you understand Bernoulli's theorem thoroughly, right, it makes it easier to understand other modules. I will clear you.
Yes.
Yes, sir.
Right, and then there's another equation for calculating HF. Right, hence I'm saying, if you are comfortable with Bernoulli's equation or Bernoulli's theorem, right, fluid mechanics will be somewhat of a breeze for you. Now, if you look at how we calculate the theoretical velocity, right, Vt being equal to the square root of 2gh, right, Vt is equal to the square root of 2gh, right? Let us take this. Right. Right. So let's consider how we calculate Vt. Vt is the square root of 2gh. Right. Now, if you were to solve for 2g in this equation, so meaning squaring both sides, and then you're left with 2gh is equal to Vt squared. Right, and then if you were to solve for 2g, or making 2g the subject of a formula, you then divide both sides by h. Hence, 2g will be equal to Vt squared over h. Right, so this next formula comes about by substituting the equivalent of 2g, being Vt squared over h. Right, so replacing 2g with this formula. So this would then be equal to HF is equal to h minus VA squared divided by this term. So in place of 2g, we replace it. In place of 2g, we have Vt squared. Right, we have Vt squared over h. Let's take this as one term. So to eliminate that denominator here, h, right, we then multiply by h, right, both the denominator and the numerator. Right, and then this and this would cancel. Then you'd have HF is equal to h minus VA squared divided by VT squared times H. Right? Now, VA squared over VT squared is the same as, it is the same as VA divided by VT, right? All squared, right? So looking at it from that perspective, you would then have HF is equal to H minus, so the H into VA divided by V divided by VT, right? All squared, right? Now remember what VA over VT is equal to. Remember what VA over VT is equal to in terms of hydraulic coefficients.
The coefficient, it's the coefficient of velocity.
Coefficient of velocity, correct. Right. So that means in place of VA over VT, right? Remember that
CV squared.
CV is VA over VT, right? So in place of VA over VT, we'll then replace it with CV. So meaning that you are also able to calculate HF using H minus H into, so you'd have CV squared, right? You replace VA over ET by CV, and we also have squared there, right? And then also taking into account that H, right? We have essentially the same term being H, right? That term is similar on both sides. Hence, you can take it out, right? And here you would have 1 minus CV squared. CV squared, right? That is where this formula comes from, right? So that is to say, yes?
So the formula for the friction head losses is dependent also on what we're given, or we can choose which one we want to use.
So it's dependent. So whichever, you can use whichever one. So I'm showing you both because how you calculate it will be essentially based on which formula is convenient for you to use, right? So meaning that if at the point where you have to calculate HF, you've already calculated VA, right? And you have H, then you can just use this, right? But for instance, if you've been given the coefficient of, say, the coefficient of velocity, then you know that you can use this formula as well.
Okay.
Right. The HF will be approximately the same, right? It will be approximately equal for whichever formula that you choose to use, right? So
but
HF,
we don't have to.
Yes.
But we don't have to derive it. Like we can just substitute whatever we calculated already and use the formula.
100%. So meaning you've been asked to calculate HF, you can either use H minus VA squared over 2G, or HF is equal to H into 1 minus CV squared, right? Okay. So yes, you don't have to derive the formula. You can just use any one of these two. Right, you don't have to use both. You can just use one. Right, any questions?
No, sir.
Leroux?
Is there no questions for me? Thank you.
All right. All right. The continuity equation, right? So in the documents I sent you, I also went through the continuity equation, right? But I only looked at how we apply the continuity equation when looking at pipes in series. So as far as the continuity equation, it will depend on if the pipes are in series. So for pipes in series, right? For pipes in series, right? So those are pipes that are essentially in a straight line. Nah, those are pipes in a
Yes.
straight line. But how we apply the continuity equation is if we have three pipes connected in series, right? Right, Q1 will be equal to Q2, which will be equal to Q3. That is pipes in series. So meaning you can use any two pipes, right, to calculate whichever quantity you might be looking for, be it the velocity. So remember, this is V1 times A1, so equal to V2 A2 equal to V3 A3. So that is if we are considering three pipes that are connected in series. Right, so you can use any two of these. So you can pair V1, you can pair Q1 with Q2, or you can pair Q1 with Q3. But depending on which quantity you are looking for, be it V1, A1, V2, A2, or V3, A3. Right, but this is how you apply the continuity equation.
Okay.
Right, the continuity equation is essentially based on mass flow rates. Right, the mass of water coming into the pipe being the same as the mass of water coming out of the pipe. Right, but how we express that mass is in terms of mass flow rates for m dot. Right, you get mass, which is m, which will be in kilograms, and then you get mass flow rate. Mass flow rate is in kilograms per second. Right, and how we calculate the mass flow rate is by using rho, multiplying that with the flow rate. Right, so m dot is equal to the rho of the fluid, so the density of the fluid times its flow rate. Right. Now, how we apply the continuity equation for pipes in parallel. Right, so pipes in parallel are pipes like, or is a pipe system like this one. Right, it's a pipe system like this one. Right, so when pipes are no longer connected in series, right, and they are connected in parallel, right, just like this pipeline system here. Right, so you have one main pipe, right, it is distributing the fluid onto different stations, for instance. Hence, the pipeline system is parallel. Right, how that affects the continuity equation is if you are again looking at, say, three pipes, right, and of those three pipes, so say you still have three pipes, right? Call this one, and then you have this one and that one. Call this two, call this three, right? Right, you still have three pipes, but of the three pipes, one is the main one, and then it branches into two. Right, so this here would be the main pipe. Right, as far as how that affects our continuity equation, it will be, so the Q1 will now be equal to Q2 plus Q3. And that is how you would then use the continuity equation. But it is very important for pipes in parallel that you are able to tell which of the pipes is the main pipe.
So they won't indicate which is the main pipe.
They will indicate.
Okay.
They definitely will indicate. Right. But your examiners like being creative sometimes. Right. So I'm thinking probably one of the ways that you can that you can tell if they haven't indicated, like if for instance they've given you the flow rates of all the pipes. Right. The pipe with the most flow will be the one that is the main pipe. Right. But for the most part, or for all problems that I've seen, right, they always indicate the main pipeline. Or maybe they won't put it as the main pipeline, but in the statement, you can tell that the fluid is coming from this pipe, right? It is distributing the fluid to these pipes. So based on how your statement is, you can tell from the statement as well that which of the pipes is the main pipe. Right? Any questions?
No, sir.
No, sir.
So you're gonna give us pipes also in the exam to parallel and series, ne? For the test, you're gonna give us pipes also, and we just have to apply that continuity equation, and then from the area velocity, depending on what's given.
I will give you.
The pipes.
Oh yes. So
Okay.
the problems in your test will be similar to the ones I sent you guys. So this one, and the third one.
Okay. Okay.
And the-
so,
and-
which one?
And the ones in the question papers, sir, that you sent, the question papers that you sent.
That is the one I'm referring to.
Okay.
It's the
I just so these problems I cropped from that question from those two question papers.
Okay. I see.
It's the same, yeah.
Yeah. So there is a third one. So make sure you do that one as well. Right.
Okay.
So I'll be available for questions going into this evening. Right. Tomorrow I'll be available for questions as well. Nah.
Okay. Okay. Thank you, sir.
Okay.
But just make sure you are able to do. Just look at the problems I have here. So these ones, you can do those to test if you understood the concepts around flow through an orifice, right? And then do those three problems, two of which I've already sent the solution. Yeah?
Okay.
And we're gonna get three questions. So
It could be more than three. It could be more than three questions, but all the questions will be from those three modules.
Okay.
So this that we did now is this module 9.
We've covered module 9, and I think, let's see, module 9 and 8.
Okay.
So the other one is fluid in motion, module 6.
Okay.
Let me see. Let me just confirm quickly. Yeah, so 6, 8, 9. Right? The modules are interrelatable because with all of them we use Bernoullis.
Okay.
But mine is 6, 7, and 8 more, but it's the same. It's all right.
Yeah. Oh yes, you with a red book, yes.
Yeah.
Have you guys have both of you done what is this, Power Machines N5?
Yes, I did.
Yes, I also did that. Yeah.
Okay. All right. So like I said, I will be available to you guys for any and all questions in preparation for the second assessment. I will mark the test. What are you guys writing Tuesday?
Tuesday or so.
Yes, the 29th.
Yes. Leroux, will you be writing on campus or online?
I'm gonna write online, sir, because we're gonna write early. I think it's at 12 or 10. We must be at campus, so I think I'm gonna write online.
Okay. And what about you, Charlene?
I'm gonna write online also. So we sailed again today, so there's no way I'll be able to go to
Okay.
campus.
So when you guys are done writing,
Yeah.
you are going to email your script to. In fact, right. Just email your script to me.
Yeah. Can you just give us your email address on the group, so please?
Yeah, I'll send you my email. Email your scripts directly to me, so I can mark them on Tuesday, and give you your marks on Tuesday.
Okay. Thank you.
Okay.
So
Are you guys doing any other subject?
I'm doing
No.
this and supervisory management.
So doing fluids and supervisory management.
Yes, sir.
Charlene?
I'm only doing fluids now, so.
Okay, right. All right, you can expect your marks on Tuesday, right? Tuesday evening.
Okay.
Right, I'll mark your scripts when I get home. Nah.
Okay. Yeah.
Okay.
Yeah.
Thank you very much, sir.
All right, cool. I will decide which module we are going to do next. Between hydraulic systems, hydraulic forces. Yeah, I'll decide which module we are going to do next. Make notes on that, and then go and then go through the module. Nah.
Okay.
Okay, sir.
Do any one of you need this recording?
I lost out, I think, the first 20 minutes.